even if the problems aren't from the previous test, I will have captured the idea that the problem captures from the previous test. Okay, so today we get to start algebra. And when you start studying algebraic structures, the first one that you study is what's called a group. So the first section, section 40, is all about groups. So that's the majority of what this is going to be about. We got to work our way up to the definition of a group, and we need to start with an operation. Now you're already relatively familiar with operations. What are some operations you know? Multiplication, addition, division, subtraction. We have some modular arithmetic. You've done function composition. That's an operation on functions. We've done operations on sets. So you've seen logic operations and or. So what's an operation in general? So if you've got some set A, an operation on A is a function whose domain is the cross product of A. Make sense?
Yeah.
That's the definition of an operation. An operation on a set is just a function whose domain is two elements out of A. Any two elements out of A. Now, typically we write operations. Well, I'll give you an example real quick of an operation. Here's an operation on the integers. So we got the function f takes two integers, gives an integer by f of a gives you the absolute value of b minus a. And we can call this the distance operation. Now typically when you see operations, you don't see them like this. We don't write plus 2, 3 is equal to 5.
Right.
Although that's a perfectly valid way to write it.
It is.
Yeah, plus is a function. It takes two elements and spits out an element. That's what it does. Typically when we're talking about operations, we put the operation, the symbol representing the operation, in between the two terms that we're operating on. So we don't typically write it like this. We typically have some special function symbol for that particular operation, and this is how we write operations. But an operation is still just a function, takes two elements, spits out an element. It's a function whose domain is A cross A when you're talking about an operation on a set. Make sense? So for example, if we were to try to explicitly write out the plus operation on the natural numbers, plus would be equal to the set 1, 1 is paired with 2, 0, 2 is paired with 2, and we can write infinitely many of them. But it's just a function of ordered pairs where the left-hand element is two elements in the natural numbers, the right-hand element is just a natural number. This is how we would write out the plus operation on the natural numbers. It's just this function. Make sense? Okay. So that's what an operation is. So let's think real quick. Which of these are operations on the natural numbers? Is plus an operation on the natural numbers?
Yeah.
It is?
Yeah.
I can add any two natural numbers? Okay, what about subtraction?
No.
Like 7 minus 100. Does that work?
No.
What's wrong with 7 minus 100?
Gives you an integer.
Is this a natural number?
Yes.
Is this a natural number? So my domain was two natural numbers. What's the definition of an operation on a set? Let A be a set. An operation on A is a function whose domain is A cross A.
But if it
Is that in the domain?
It doesn't give you a.
We didn't say anything about the codomain. We didn't say anything about the image. We didn't say anything about the range.
Okay.
So yes, this is an operation on natural numbers. The fact that the result of the operation is not a natural number does not stop it from being an operation on natural numbers. Make sense?
Yeah.
Alright, what about times? Is that an operation on natural numbers? What about divide? Almost.
You can't divide any two. Well, I guess there's zero.
What's wrong with this?
Yeah, there's zero.
It's not defined. This doesn't go to anything. This isn't in the domain of the divide function. So the divide functions function's domain is not n cross n. It can't have 0 in there. It's not defined as 0. Does that make sense?
Yeah.
Yeah.
So this has to be the domain, the whole domain. The domain can't be a subset of this. It has to be this. So this would make this, we could say that division is an operation on the set, the natural numbers minus 0. Okay, now division is an operation on this set, but when we have 0 in there, division is not an operation on that set. Make sense? Okay. Now in algebra, a lot of times we're not going to be interested in a particular operation. So you got to get ready to take a leap in your mind here. The same way that you had to make a leap when you went from basic arithmetic to pre-algebra, then you have to make that leap of, I'm no longer talking about a particular number, I'm talking about x, a variable. And the variable represents any number, right? Well, we're going to be doing something similar with star representing any operation. We're going to be talking about operations in general now. And we're going to be talking about properties of operations in general. Okay? So star is the symbol that I'm going to use from here on out as a general operation. It's not plus, it's not times, it's not divide, it's just an operation. Just like x isn't 4, it's not 2, it's not 6, it's just x, it's a variable. It's just an operation. Make sense?
Yes.
Okay, so that's what we're going to often be doing. We're going to be talking about properties of operations and what you know about operations given certain properties. So definition. Let star be an operation on A. We say that star is commutative. I always do that. I don't know why I do commutative. Commutative, provided that for all AB in the set A star B is equal to B star A. You're very familiar with the commutative property, right? Okay. Again, we say that star is closed on A, provided that for all AB in A star B is also an element of A. You proved like modular addition was closed, for example. That was a particular operation that you proved was closed. You proved that if A is in Zn and B is in Zn, then A mod addition B is also in Zn. You remember that? Or maybe you did with time. I don't remember which one you did it with, but you did it with one of them.
We can do it two of them.
We did it with 2 of them. Okay. So that's what we mean by operation is closed. The range or the image of the operation is the set A. Or is a subset of set A, I should say. Okay, associative. We say that star is associative, provided that for all A, B, C in A star B star C is the same thing as A star B star C. And then finally, we say that E in A is an identity element for that operation, provided that for every element in the set, A star E is equal to E star A is equal to A. So for example, you know that 1 is the identity element for multiplication on the real numbers. A times 1 is equal to 1 times A is equal to A. You know that 0 is the identity element for addition on the real numbers. You know that A plus 1 is equal to 1 plus A is equal to A. You know that true is the identity element for or on the set of booleans, true, false. Any boolean or true is equal to or false. False is the identity. Anything or false is equal to false or anything is equal to that thing.
Oh, yeah.
X or true, or not true, X or false is equal to false or X is just equal to whatever X is. If X is true, all those statements are true. If X is false, all those statements are false. And you can do a similar thing for and true. So true is the identity element for and on the set of booleans. Make sense? So when we're talking about a general identity element for a general operation, we typically use E. That's a terrible E. Okay, so any questions about any of these properties of operations? Here's some general properties that we're interested in. All these make sense? All right, continuing. Okay, so let's do our first proof. Let's prove that if star is an operation on A, then star has at most one identity element. Now, we've already proven this for special cases, I think. Maybe we've never done this one before. But it's a pretty straightforward one. And this is something standard that you would do like at the beginning of algebra. Prove that algebra is a unique multiplicative identity element. There's only one number that has the properties that one has. Oh well, doesn't matter. Let's just go through this proof. So assume by way of contradiction that there are two identity elements in A, that are identity elements that aren't equal to each other. And we're going to show this leads to a contradiction. Then E is equal to E times E prime. How do we know that? E prime is an identity element. So E prime times E, since E prime is an identity element, that's just E. But since E is an identity element, E times E prime is just E prime. So E equals E prime. Contradiction. So you can't have two identity elements for an operation. You can only have one. Make sense?
Wait, no.
No?
They're both. I'm saying use what?
So remember what we're proving. So star sum operation. We're proving that for any operation, then it has at most one identity element. It's impossible for it to have two or more.
Right.
So we assume by way of contradiction that there are two identity elements for star. So two that aren't equal to each other, and we get that they are equal to each other. Contradiction can't be the case. Good? Okay. Definition. Let star be an operation on the set A with an identity element E, and let A be any other element in A, could also be E. A is just an element of A, big A. We call B in A the inverse of A, provided that A star B is equal to B star A is equal to E. Okay? Let's think about some inverses that we know of already. So if we're thinking about addition on the integers, what's the inverse of 5? Negative 5, right? Because 5 plus negative 5 is equal to negative 5 plus 5 is equal to 0. The identity element for addition. Let's think about.
Okay.
Let's think about multiplication on the real numbers. What's the inverse for 2/3? 3 halves. Because 2/3 times 3 halves is equal to 3 halves times 2/3 is equal to 1. Make sense? So that's what we mean by an inverse. So if B satisfies this for A, then B is an inverse of A. And you might remember when we were doing modular arithmetic, when we were doing multiplication in particular, we ran into a problem. We ran into the case where sometimes there were multiple inverses for a number. You remember that? So we have the case up here where if there's an identity element, there's only one identity element, But here, we're going to find out just because there's an inverse doesn't mean that there's only one inverse. Here's an example. So, let star be an operation on this set. Here's star. And you need to get comfortable with graphs like this. This is just like a multiplication chart or an addition chart. It's doing the exact same thing. It's saying E star E is E. A star A is A. B star C is E, etc.
How do we come up with charts like that?
There's no difference between that chart and like a multiplication chart. It's doing the exact same
What are you
thing.
talking about?
Or an
That
addition
makes
chart.
no sense. That chart makes no sense. How did you write that?
Okay. Multiplication. I can write the numbers 1, 2, 3, 1, 2, 3. And I can start writing a product here. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. 1 times 2 is 2. 1 times 3 is 3. 2 times 2 is 4. 2 times 3 is 6, etc.
Right.
So just
So
a
how do you
multiplication
know
chart.
what A star B is?
This is defining star for you.
Oh, okay.
This is, because we could have written out this function, right? We could have did parentheses, E comma E goes to E, A comma C goes to E, and we could have written it all out, but this is a much cleaner way to look at it. The same way that we could have written out multiplication as a big long function, but multiplication chart's nice. So this is just defining star. There's no reason that you should have known off the top of your head. Oh, so B star C is E, obviously. No, this is a definition. I didn't derive this from some previous knowledge. It's just a definition of what star is. Make sense?
Yes.
So, here we go. So we've got this set, we've got this operation defined on this set. Notice the way that this operation is defined. Well, first off, notice that E is the identity element in this operation. E started with anything, it just always gives a thing that it started with. So E is an identity element. And then notice that A star B is equal to B star A is E. A star B gives you E, or A star B gives you E. Either way, it gives you E. Same with A star C. So B is an inverse element of A, and C is an inverse element of A. That's a problem. Well, I should say it's a problem, but not very nicely behaved. We would like operations where they have unique inverses. It's nice to work with those operations. So operations don't have that property in general, whereas operations have this nice property in general. So the question is going to be, what property does an operation need to have to guarantee that it has a unique inverse? And the answer is going to be, it has to be associative, but we'll get to that. So, just note this problem and we'll fix it once we come up with a definition of a group. So, moving on to the definition of a group. Let star be an operation on some set G. The tuple with the set and the operation that the set is defined on is a group, provided that star is closed, star is associative, star has an identity element in G, and then every element in G has an inverse element in G.
Can you give us an example?
Sure, addition on the natural numbers. So when you add two natural numbers together, do you always get a natural number?
Yeah.
So addition is closed on the natural numbers. We already know addition is associative in general, right? So addition is associative on the natural numbers. Do the natural numbers have an identity element for addition?
Yeah.
Yes, 0.
Yeah, I see that.
Oh, but this one doesn't work.
Yeah,
So yeah, I lied. It's not.
it is on the integer.
On the integers is what I should have said. So addition on the integers is a group. Make sense?
So what, then Z
Yeah, that's just really weird. That's very
star
notation.
would be a
Yeah, so a set along with the operation on the set.
An operation is a set, basically.
An operation, right. Remember, all mathematical objects are sets of some sort. An operation is a special type of set. What type of set is it? Well, it's a special type of relation called a function, but it's a special kind of function called an operation. So its domain we know is G cross G in this case. So it's a function whose domain is G cross G, is what star is. You'll notice that this is really similar to how we define like a sample space.
Yeah, it is.
Right? There was a set of possible outcomes and a probability function whose domain was a set of possible outcomes. Well, now this is a group. We've got a set and a function whose domain is this set cross itself. Right? Good so far with that?
What does cross itself mean?
Like this. A cross A.
Which means what?
The Cartesian product, it
No,
means
I know.
the set of all possible
Times.
outcomes.
Okay.
Not times. So for example,
Right, 1, 2, 3.
1, 2, cross 3, 4 is equal to the set 1, 3, 1, 4, 2, 3, 2, 4. Set of all the possible ordered pairs you can get where all your left-hand elements come from here and all your right-hand elements come from here. Good? So, when I say that star is a function whose domain is G cross G, that means star is a function that can take any two elements in G.
Okay.
Does that make sense?
Yes.
Okay.
So dumb. Yes.
I don't know why it's done. Okay. So you have a set and you have a function whose domain is G cross G, is that set cross itself. And this tuple together is called a group, provided that this function here is closed on G, is associative, has an identity element in G, and that G has an inverse element for every element in G.
So it's only a group if it has all those things.
Yes, it's only a group if it has these four properties. Good? Okay. And then we have a special type of group. A group G star is called an abelian group, provided that the star operation is also commutative. Because notice over here we only guaranteed if it was a group, oops, we only had that was associative. So if the operation is also commutative, then it's a special type of group called an abelian group. Good so far?
Yeah.
Okay. So now once we have a group, since the group has this special property of associativity, then we're going to find out with a group, every element has one and only one inverse element. So let's do it. So every element of G in that group has a unique inverse. Now we already know it has one inverse since it's in the group. That's what property 4 says. Every element has an inverse. So we already know it has an inverse. So we just need to show it's impossible for it to have two inverses, and we're done. Make sense?
This is basically the same group we just did.
Almost identical. So assume by way of contradiction that there exists an element of G with two inverses that are different from each other. They're not equal to each other.
What does an element of G look like?
What does that look like?
Yeah, like how would you write it out explicitly? If you had a group, how would you write an element out of it?
Well, the group is this thing.
Yeah.
And when we say an element in the group, we really mean an element in the set that the group is defined on. So when we say an element in the group, we really mean an element in G.
Okay.
Because the group has two elements. It has this set and this function.
So isn't that, wouldn't you be saying B and B inverse is a G? Why is it A and G? Oh, okay, never mind, I got it.
Okay, because I didn't understand your question. Okay, so assume by way of contradiction that there is some element in G that has two inverses that aren't equal to each other.
Right.
And we're just thought this leads to an impossible situation. Then B is equal to B star the identity element, right? We start the identity element, you didn't change it. But since, I didn't mean to do a negative one there, I meant to do a prime. Sorry, that was probably confusing. Okay, sorry about that. Now since B star, or B prime and A are inverses, then A star B prime is just the identity element, right? That's what means for them to be inverses. That make sense? Okay, so replace that with A times its inverse, A star its inverse. And now, because of associativity, we can go from this to this. Right?
Huh.
Okay, wait, back up. Yeah,
Going from here to here.
yeah.
So the definition of, where did we write that?
Oh, wait, no, never mind, okay.
Oh, you're good.
Yeah,
Because B prime is an inverse of A.
right.
Okay. So you replace E with A times B prime. I keep saying B inverse, jeez. Replace E with A star B prime. And then because of associativity, we can go from here to here. Since B is an inverse element of A, we can replace that with the identity element. The identity element started with anything is just that thing. So we got B is equal to B prime, contradiction. Good?
Mhm.
So that's like a generic template for if I said prove that 2 doesn't have two inverse elements when with addition. You could follow that exact kind of template. I know you're not used to doing those kind of
How would
types
you
of proofs.
do that?
Assume by way of contradiction that 2 has two inverse elements of addition. Name them. What do you want to call
B and B prime.
them? B and B prime. Or maybe we call them, sure, B and B prime. Then I would say that 2, well, then I would say B is equal to B plus 2 plus B prime is equal to B plus 2 plus B prime is equal to B prime. And that's how we know that 2 only has one inverse element, namely -2. Because that's how, when you're constructing the integers, that's how you define your negative numbers. Well, I guess you don't have to, but that's one way to do it. You define your negative numbers to be the additive inverses of the natural numbers. And so that's what -2 is by definition. It's the additive inverse of 2, and we know that there's only one, so that's a unique number. So it's well defined when we say -2. We're talking about one number. So there we go. So if an element has an inverse, it only has one inverse. It's unique. We typically denote the inverse of A as A to the -1. That's the typical way to do it. There's all sorts of there's exceptions to the rule. Like, for example, we don't do the inverse of 2 as 2 to the -1. We do that as -2. But when we're talking about inverses a lot of the time, this is how we do it. Good?
Yeah.
Just typical, but there are exceptions to the rule. Okay, so let's go through a few examples and see when we're talking about a group and when we're not talking about a group. So if we're talking about Z with addition, is that a group, yes or no?
Yes.
Yeah? Yes, that's a group. Okay, what about the rationals with addition?
Yes.
Every element has an inverse element with addition.
Yes.
What's the inverse of 0? Just 0. So yeah, we're fine.
Yourself?
Yeah, nothing wrong with that. So yeah, perfectly fine. Okay, what about the rationals and multiplication? Is that a group? Let's think through each of these. Is it closed? When you take two rationals and you multiply them together, do you get a rational? Okay, so that seems to work. Is it associative?
Yeah.
Yeah. A times B times C is the same thing as A times B times C. Does every element have, or does it have an identity element for multiplication?
1.
1. Yeah, 1's in the rationals. That works. Does every element have an inverse?
Yes.
What's the inverse of 0?
It's the multiplicative. Oh, 0?
Yeah.
Oh.
0. What?
What's the multiplicative inverse of 0?
It doesn't have one.
It doesn't have one.
That's right.
How?
There is no number you can find. In order for it to be an inverse, what does it have to satisfy?
Oh, it has
0 times b has to equal b times 0 has to equal 1. That's what it means to be an inverse element. So if b was an inverse element of 0, it would have to satisfy this. So you'd have to get a b that satisfies that.
Right.
And b times 0 is 0, not 1. So there are no numbers that satisfy that. So no, this is not a group. Oh shoot. What about if we got rid of 0? Then is it a group?
Yeah.
Yeah.
You sure?
Yeah.
Yeah.
What's the multiplicative inverse of 1?
1.
1. Okay, so yeah, it's all working. Alright, you guys might have lost track of what this represents. There you go. The set of all permutations on an n element set. And we're talking about composition. Function composition.
Oh boy.
Oh boy.
What's its identity element?
The identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, n goes to n. If you take some permutation and you compose it with the identity permutation, it doesn't change it.
Right.
So, but let's go through each of these.
So what's the inverse?
The inverse is the permutation that takes it back to the identity permutation.
So it's just the two things flipped?
Not necessarily. But, oh, just the two things flipped is a way to think about it, yes. Like an inverse function.
Okay. So then it
Right? So 1 mapped to 2, so in the other case 2 has to map to 1. Yes. Okay, but let's go over it. So composition. If I take two permutations and I compose them together, do I get another permutation?
Mm-hmm.
Yes. Is it associative?
Yes.
Yeah.
Composition is associative?
It has to be.
Is it commutative?
No.
No. Associative but not commutative. That's right. So yeah, you're right. It is associative. Does it have an identity element? Yes. The identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, etc. And then, does every permutation have an inverse permutation?
Yeah, we just said
Yeah. You just flip all the elements places. Right?
Mm-hmm.
Okay, I'm thinking of like.
Let's just draw a picture real quick
Okay,
to
so
get it.
wait, hang on. So 1, 2, right? Like this at 1, 2, 2, 3, 3, 1. Isn't that right? 'Cause
That's an example of a permutation for S3.
1, 1.
So you usually said 1 goes to 2, 2 goes to 3, and 3 goes to 1.
Can you redefine a permutation, please?
A permutation is a bijection from the set 1 through n to the set 1 through n. Bijection being 1 to 1 and on 2. Good?
Yeah.
Okay, so here would be an example of a permutation in S3.
Right, but
What's its inverse?
isn't that an inverse? Or isn't that the identity one?
No, the identity is just 1, 1, 2, 2, 3, 3.
Okay.
So the inverse of this then,
Yeah, but eventually
Is-
1 goes to 1 in that.
2, 1, 3, 2, 1, 3. Because look at what happens when you do the function all the way through itself. This function takes 1 to 2, but then 2 goes to 1. Oh, so 1 went to 1. This function takes 2 to 3, and then 3 to 2. Okay, so 2 went to 2. So when you do this function composed with this function, then you just get the identity permutation.
Okay, but
So this
also,
composed with this.
isn't that also, the top one, isn't that also an identity element?
No, the identity permutation, which would be the identity element in this case, is this one. That's the identity permutation in this case.
Oh, I'm talking about, wait.
Compose any function, compose any permutation with this permutation, and you didn't change it. Make sense?
Yes.
And there's only one identity element, or one identity permutation, via this. And I think that was one of the proofs that we explicitly did. We proved that there was only one identity permutation. And we did a proof exactly like this. Make sense? You remember what that S, N, and compose is?
Yes.
Okay, and yeah, that's a group. Nice. Alright, what about Zn with addition?
Yeah.
Modular addition, I mean, sorry.
No.
Let's see. Is it closed?
Yeah. Yes.
Yes. You can't do modular addition and get something outside of Zn. Right?
Right.
Because you do the addition, then mod by n. You proved it was closed, I think. Maybe it was for multiplication. Is it associative?
Yeah.
No.
It's not?
It's not. Yes. No. It is.
It is. Think about what it is by definition. By definition, it's using regular addition behind the scenes. Regular addition is associative, so it has to be associative.
Right.
Right?
Yes.
Okay? And I think that's also one that we proved. Does it have an identity element? Is 0 always in Zn?
Yes.
Yes, 0 is always in there, and 0 is the identity element for modular addition.
Okay.
Does every element have an inverse?
No.
Yes,
What?
every element has an inverse. Pick an element and first off pick n,
200.
200. Now pick any element out of there and I'll tell you its inverse.
15.
15. So 185. 185 plus 15 is 200. Mod 200 gives you
Oh.
0.
Oh.
It's the unique number that you need to add to it to get back to 0.
That's.
So it's not one.
That's the
No, this
inverse.
is- That's modular multiplication. No, it isn't. That's addition.
No, that's addition.
I think. Okay, I got it. Okay.
Isn't it the same?
Yep. So we all on the same track now?
Yeah, I was thinking
You understand how?
for modular multiplication, it's not inverse.
Right. Jumping the gun a little bit. Next, Z10 and modular multiplication. Is this a group? So we said yes here. Here we jumped the gun already. Said no, it's not. Why? Because not all the elements in here have an inverse for multiplication. In fact, we had some theorems. When does an element have an inverse?
One equals like one.
When it's relatively prime with this thing, right? Remember?
Is that
So I know 2 and Z10 doesn't have a multiplicative inverse.
right? And then right, I did. Yeah, we had to do some problems like that.
Good? Okay. Alright, let's look at this one. So here's my set. G is the set of these tuples, ordered pairs, sorry. And then here's the operation star. Now what is star doing? It's adding the elements, so it's taking A plus C mod 2, and B plus D mod 2 is what star is doing. So when you do 1, 1 plus 1, 1, 1 plus 1 is 2, mod 2 is 0, 1 plus 1 is 2, mod 2 is 0, for example. You understand the chart?
Yeah.
Is this a group?
Wait.
No.
I'm
Let's go over it.
when you're adding ordered pairs.
Are all the outputs in G?
Yes.
Yeah, all the outputs are in G, so it's close. Is it associative?
Yes.
Are you sure?
Yes.
Wait, what?
Wait.
Are we doing
Yes.
addition?
Yeah.
We're doing
Yeah. Social.
this operation star. What does star do? Well, here's a table for what it does. This star this is this. And yeah, it's associative. Okay. Does it have an identity element?
Yes.
What's the identity element?
0, 0.
0, 0 is the identity element. Notice 0, 0 with this just gives that thing. 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 Same with up here. So this starred with 0, 0 is this. This starred with 0, 0 is this. So on either side, because remember for an identity element, you have to be able to do it both ways. Both ways it always gave out. Oh, two.
Shouldn't this, when you
That's not the identity element.
define your addition, wouldn't it be A plus
Right
C?
here, no.
This. Huh?
When you're defining your operation, shouldn't it be
Yes, it should. Good catch. Okay, so it has an identity element. Finally, does everything have an inverse?
yes.
Yes? What's the inverse of 1, 1?
1, 1.
1, 1. What's the inverse of 1, 0?
What's that? What's an inverse?
Huh?
0, 1?
No, just 1, 0. Everything is its own inverse. This star with itself gives the identity element. This star with itself gives the identity element. This star with itself gives the identity element. This star with itself gives the identity element.
Okay, that makes sense.
I see.
So everything's its own inverse.
Right.
So everything's its own inverse. So everything has an inverse. So yeah, it's a group. Right? Wonderful. Okay. Now let's take care of the problem we ran into up here. We don't like that this isn't a group. Could we somehow take a subset of this thing and end up with just a group?
Yeah.
Right? The same way, look, if you took, so multiplication on the rationals, that didn't work, but if we just got rid of the 0, now it worked. Well, similar question here. Is there some way that I can remove some elements from that thing to finally get just a group?
Yeah.
What elements do I remove?
All the ones that don't have inverse.
All the ones that don't have an inverse. That's exactly right. So let n be a positive integer. So first we gotta make a definition for the type of, for exactly what you just said is what we're gonna define. So if n is a positive integer, then zn to the star is equal to z sub n. Every element is e sub n that's relatively prime with n. But it's doing exactly what you're saying. Get rid of all the elements that are relatively prime.
You're kind of just coming up with the definition for z sub n star.
Yeah, we're defining what this symbol means right now.
Okay. Is that pretty universal notation?
Yeah. So it's z sub n, get rid of all the elements that don't have an inverse. That's what z sub n star is.
Or all the elements that don't fit what you want it to fit. It doesn't necessarily have to be inverse, right?
out all the ones that aren't relatively prime with this thing, which
Right,
turns
so-
out is the same thing.
What I'm saying is, if you had a different situation, like one with the rationals, you could define it the same way and give it just a different set. Right?
This is only used in the context of Z. The same way that the Z sub n only made sense in the context of Z. We didn't have Q sub n.
So this is always is talking about inverses then.
This is always talking about a subset of this thing. Z sub n is a set. What's Z sub n? It's the integers mod n. This is the integers mod n, removing all the ones that aren't relatively prime with n. We're only keeping the ones that are relatively prime with n.
So my question is, could you do something like Q star equals everything but 0?
You could, but no one does that.
Okay.
This is universal notation for this context. The same way that Z sub n is uniform, is notation for this context.
Okay.
Okay, so let's just make sure we understand exactly what we're talking about. So what's Z14 star? We know what Z14 is, right? Z14 is what?
0 to 13.
0 through 13. So Z star 14 is all the elements in 0 through 13 that are relatively prime with 14. Which are these? Good?
Mm-hmm.
Why isn't 0 in there?
Because it doesn't have inverse.
What's the greatest common divisor of 0 and 14?
Isn't.
There is one. It's 14.
14.
Yeah.
Oh yeah, right.
And in order for it to be relatively prime, the greatest common divisor between the two numbers has to be 1.
Right.
What's the greatest common divisor between 1 and 14? 1. Greatest common divisor between 3 and 14? 1. Greatest common divisor between 5 and 14? 1. Etc. That's the numbers that we kept. The ones that are relatively prime with 14. Make sense? Okay. So, notice now, writing out the multiplication table for this set, we kept just our elements that had inverses. And here's how the multiplication table comes out. Notice every element has now an inverse. So now we have a group. So let's prove that we have a group. So we're going to prove that Zn star in times is a group. Which means we need to show it has these properties. So first we need to show it's closed. Good?
Okay.
Alright, so let's show that it's closed. So grab two elements out of there. We grab two arbitrary elements out of there. I need to show that A modular times B is also in the set, and that shows it's closed. Right?
Mm-hmm.
You understand what we're doing? Okay, so let's do it. So since A and B are both in Zn star, then what does that mean? That means that they're relatively prime with respect to n. So that means A times an integer plus n times an integer equals 1. And that means B times an integer plus n times an integer equals 1. Remember that?
Mm-hmm.
And that was, I told you, the second most important theorem in number theory that we were dealing with. And I told you it was going to come up again and again, and it's never going away. So that means that there exists x, y, z, w in the integer such that ax plus ny equals 1, because a and n are relatively prime. And there exists b, z, and w such that b times z plus n times w equals 1, because b and n are relatively prime. So 1 is equal to 1 times 1, right?
Mm-hmm.
Is equal to, we're just distributing. I rewrote the order so that the n's came at the start of each of these terms, because I'm going to factor out n out of all those. So going from here to here, I just factored out the n from those three terms. But the point is, I have 1 equals an integer times something plus n times something. So ab times an integer plus n times an integer equal 1. Which means ab and n are what? Relatively prime. So a times b and n are relatively prime. Therefore, a times b and n are relatively prime. So a times b other words, when you mod it by n, when I mod both sides of this by n, it's still going to be true. And mod by n is exactly what this is. This is a times b mod n. Still going to be 1, so still relatively prime. Okay. Therefore, times is closed on this set. So we showed it was closed. Is it associative? Yes, we already proved that this was associative in general.
One.
It was one of the 4 properties that we listed for this.
Huh.
Right? We had to do.
So it's associative when the operation is associative.
Yeah, this operation on all integers is associative, commutative, distributive, or you can distribute it with addition, and it has identity element. So we've already done that. Does it have an identity element? Yes, 1 is always in there. Is 1 always in this set?
Yeah.
Yes, 1 is relatively prime with any positive integer n. So 1's always in the set. Make sense?
Did you give the definition of that?
Of the zn to the star?
Yeah.
Yep.
Sorry, I missed that. What was it?
Right here. It's zn, it's all the elements in zn that are relatively prime with respect to n. So their GCD is 1.
Okay.
So
Right.
Z14 star is all these elements. Make sense? And then, oh,
Sorry. Just want to re-clarify. For Z and star, is that definition always that way, or can you change what's on the right hand side of that equation?
it's always that way.
Okay, so it's always what's relatively prime in Zn.
Yes.
Okay.
Okay, and then the last thing we need. What?
Wait, what did you just say? Are you saying Z and star is always that? Like that's what Z and star means?
So you're gonna pick
That's what
an
it sounded like.
you're gonna pick an n here, a positive integer, like 14. So Z14 star is always all the integers less than 14 that are relatively prime with respect to 14.
Okay.
So pick all the integers less than 14 where the GCD of those two is 1.
I get it, but
That's what Z star always is, with that subscript n. Z sub n star is always all the integers less than n relatively prime to n. I don't know how else to say that.
makes sense.
Okay.
It's just surprising.
Oh,
Whatever.
okay. So now the last part. We need to show that for every element in Zn star, it has an inverse element. And if it does, then that's a group. So let's prove that last part. So pick some element out of Zn star A. We need to show that it has an inverse element, and that the inverse element is also in Zn star. And we're done. This is a group. Make sense?
Mm-hmm.
2 things. Show it has an inverse element. Show the inverse element's also in the set. And we're done. So we're going to start by showing that A has an inverse element. Well, since the GCD of A and n is equal to 1, we know that A has an inverse element, A inverse. That's from the last section. How do you know, right, when you're solving a linear equation, if I had 3x is congruent to 4 mod 10, how did I know that I could do that? How did I know when 3 had an inverse? When 3 and 10 were relatively prime.
Right.
Right.
Oh.
So,
And these are relatively prime.
since A and n have a GCD of 1, they're relatively prime, and so we know they have an inverse element. Or we could use that equation that we talked about. Extended Euclids is how you find that relatively prime number, but nonetheless, it's relatively prime. We've already known that.
Right.
So now the question is A inverse in this set? That's the question. Since A inverse is invertible, we know that A inverse is relatively prime to n. We show it as an if and only if. If they're relatively prime, then it has an inverse, and if it has an inverse, then they're relatively prime. Make sense? Which is, finishes it off. So therefore it's a group. And then that stuff under ignore, I was doing something else. So that is the beginning of algebra. Next next week we do review, and then spring break, and then final.